Thank you very much indeed. Yeah, so in fact, you can see immediately, this is actually a talk from two people. So Sabine, I'm sure many of you know Sabine Howard, or if not her, you might know her work. In fact, Sabine actually is in New York right now for the DARS conference, which I used to go to, Distributed Autonomous Robotic Systems. And as Mohsen said, this is a brand new talk. It's unusual these days for me to write a talk from scratch. But in fact, the title of the talk is the title of a new paper that Sabine and I submitted a few months ago. It's currently in revision, so we've had reviewers' comments back, and that is the title. So, what am I going to be talking about? What's the kind of shape of the talk? Well, this is an outline of the talk. Now, I should say that I'd like this to be a discussion, not just me talking. So if you have any questions or comments or suggestions even, no, that's a crazy thing to do. Why don't you do this instead? Please stop me, during the talk. Don't feel you have to wait until the end. So I'm going to start by asking, why do we need ethical governance for swarm robotic systems? Then I'll introduce some beautiful safety principles for swarm systems. I'll then introduce ethical risk assessment because I think it's an extraordinarily powerful tool, perhaps the most important ethics tool in robotics that there is, robotics and AI. And I'll finish with a framework, proposed framework. And I should also use the word draft. So even though we've submitted this big journal paper, quite a long paper, I think we're the first ever to even think about the ethical governance of swarms in the real world. And that's an important thing. So the framework that we're setting out is, of course, a draft framework. I mean, it's untested. And I'd love it if one of you might, decide to take up that challenge and actually apply the framework. And and as we go through the talk, you'll pick up some hints as to how that might actually work. So that's the kind of shape of the talk. I don't have a lot of slides, but they're quite dense. And I'm going to take my time because we're not in a big rush, which is very nice. So, okay, let's dive in. Why do we need ethical governance? Well, let's make, I think, a reasonable assumption that swarm robotic systems will be applied in the real world within 10 years or so. I mean, there are already companies, for instance, my friend, you probably know Vito Triani. So he has a company that is developing swarm robotic systems for agriculture, precision agriculture. So, the point is that we have the technology pretty much for swarm robots in the real world, especially flying swarm robots. And some land and certainly some marine swarm robots. We have the technology to build all of those. But of course, if we do, then we have to ensure that such systems are designed, built, and operated responsibly. So really what I'm talking about here is responsible robotics. So you may be thinking, if you're familiar with the literature of ethical governance, we have existing frameworks of ethical governance in conventional single robot systems. There's a paper that I published in 2018, so 6 years ago, with a colleague on ethical governance in building robotics and AI systems. So there are existing frameworks, but none of those frameworks address swarm robotic systems. And I think the reason that we cannot apply existing frameworks exactly as they are, in other words, take them precisely off the shelf and apply them to swarm robotic system, are these three words: emergence, autonomy, and scale. And those are the three properties, if you like, that I believe, Sabine and I both believe, are kind of unique to swarm robotic systems. So let's start with emergence. So unlike, and you can see that in my first draft of this slide, I wrote almost any other engineered system. I've crossed it out because, you know, I've been building engineered systems. I spent the first 10 years of my professional career building safety critical systems in industry. And I don't believe I've ever come across an engineered system where emergence is a good thing. The truth is that in conventional engineered systems, I mean, and you know, I can tell you I've encountered plenty of emergent properties, but they were a bad thing. Emergent properties in conventional systems are bugs that need to be fixed. So swarm robotic systems are, I think, probably unique in the sense that emergence in swarm systems is not a bug, it's a desired property. It's part of the way the system works. And of course, you're probably very familiar with this very nice diagram that, you know, that kind of nice graphically explains what emergence is. Local interactions which change the global structure, which in turn prompt more local interactions. So it's this emergence is a very nice closed loop kind of feedback property that we see, of course, in social animals, social insects in particular. But of course, as you know, designing swarm systems that harness self-organization in emergence is challenging. Why? Well, there are many reasons. I mean, designing emergence is hard, and for one thing. That's one of the reasons that that evolutionary swarm robotics is such an interesting area of swarm robotics, because there we evolve the emergent properties as opposed to hand design them. I mean, hand designing emergent properties, and I've done a lot of this, not so much recently, but certainly 20 and 30 years ago. It's challenging, and one of the reasons is because swarm systems are typically stochastic. So, you know, we can't predict, even for the same starting conditions, where the robots will be after some time. That's absolutely true, of course, of real robots, even identical real robots, because you all know that identical real robots are not really identical. So the small heterogeneities, the small differences between identical robots mean that there is stochasticity, simply because of the, in a sense, natural heterogeneity. And I use the word natural quite deliberately, of course, because animals that are conspecifics are also all a little bit different from each other. Even clones like, you know, ants, are still slightly different because of physics. You know, their sensors are not identical. Their muscles and legs are not all identical, so they all behave a little bit differently. And, you know, I don't want to go off into a whole other talk, but I think that stochasticity is an absolutely necessary aspect of the emergence of life. I think stochasticity is, if you like, the grain of sand, and this is an analogy, that creates a pearl. You know, the pearl is life. Stochasticity is the grain of sand, a little bit of irritant, you know, that is exploited by self-organizing systems, and life, of course, even singular life. Yes, please. Okay, so emergence, I think, is the first property of these three properties that make it hard to govern, if you like, to responsibly develop swarm robotic systems. The second one is autonomy. And of course, as you know, a notable property of swarm systems is the unusually high level of autonomy of the individual robots. Yet, real-world swarms, and that's what we're talking about here, must be subject to human monitoring, oversight, and, if necessary, intervention. Now, that seems kind of wrong. If you've spent years, as I have, working in a lab with swarm robotic systems, you just switch them on and let them do their thing. And, when the battery runs out or the batteries run out, eventually what they do, then you stop and you analyze what's going on. So there is no human intervention. Well, of course, that would be utterly, utterly irresponsible for real-world systems. So we really must treat real-world swarm systems as what I call socio-technical systems. All robots, I would argue, all robots are socio-technical systems. Even, the robots wandering around on Mars, maybe a very long way away, but they are part of a big science project. So, the idea that these autonomous robots have no human interface or human interaction is absurd. So I really do think we need to treat real-world swarm systems as socio-technical systems. And the third, of course, is scale. And depending on the application, of course, swarm systems may have tens, thousands, or in the case of nanomedicine, millions of individual robots. So that really means that that human swarm interaction is very difficult. Human swarm interaction has been around for a long time. I've known people like Luca Gambardelli and Richard Vaughan, pioneers in human swarm interaction, working 20, 30 years ago. But they were dealing with small swarms where they could literally have a human being, pointing at robots and essentially directing them as to what to do, even though they're autonomous swarm robots. But when we have very large populations out in the real world, I think we will need new approaches to understand, monitor, and control large populations of robots. And of course, human swarm interaction is necessarily very different to approach, different to the way we do human robot interaction, which is typically concerned with one-on-one interactions. Here, we'll be concerned with maybe one or a team of human monitors overseeing potentially thousands or millions, perhaps, of robots. I often think about this in the context of shepherds. So, you could almost think of the human monitoring or oversight of a swarm of robots as shepherding. The humans are shepherding the robots and, in a sense, looking for the outliers, looking for the ones that are kind of gone a bit crazy. In fact, some years ago, I submitted several with colleagues, including, I think, Verena Hafner, failed European Union bids where we were proposing methods of human swarm interaction that would exactly follow that metaphor of shepherds, of shepherding their flock of robots. And in fact, using sound, whistling. This is what we were proposing. It was a crazy proposal, but often crazy works. So I think it's not a bad metaphor. So that, I think, is the third big reason that we cannot use existing frameworks for ethical governance of swarm robotic systems. So this is a beautiful paper, if you've not seen it, by Edmund Hunt and Sabine It's a very short paper. It was published in Nature Machine Intelligence in 2020, and it's a set of safety principles for swarm systems. It's very straightforward, but I think the analysis and the list that Edmund and Sabine came up with is brilliant. And essentially, the table has an issue and a question. So, and you can see the first one is just labeled ethics. Is this an ethical use for swarm? Well, that's a big question. That's a question without a single answer, or it's a question that requires some analysis. It's not a simple question typically to answer. And I'll come, in a sense, elaborate more on that as we go through. Another very important one, legal. Does the swarm comply with laws and regulations? Now, a lot of roboticists, particularly my students, are under the strange impression that laws and regulations don't apply to robots. Well, they may not apply to robots in the lab. That's not entirely true because, of course, university labs require ethics approval if you're interacting with humans, and also require that the robots are safe for humans to be around. So, there are rules, but any artifact that is used in the real world will, in fact, have existing laws and regulations applied to it. So you mustn't assume that because you've invented this fabulous new swarm of robots that it's automatically legal. So that's a really, really important question. Accountability is another very important question. Is there a way to analyze swarm failures? Again, that's a very big question. And it's a question that I've spent perhaps the last 6 or 7 years of research working on. And I'll tell you a little bit about the project that has been addressing that particular question. Is there a way to analyze swarm failures? Now, swarm failures, of course, are harder, I would suggest, to analyze than failures of a single robot. Again, we can talk about why, but number 4, user interaction. Can users interact with the swarm to prevent unwanted behavior? I think the word users could be interpreted several ways. Some of the case studies that we have applied in the paper that I'm essentially drawing upon, the not yet published paper, will have human users in the straightforward sense. But all of the swarm systems in the real world will have humans interacting in the sense of monitoring and intervening if necessary. So can you do interaction with both individuals in the swarm, if that's appropriate to the application, or the entire swarm? Then there's a set of another 6 properties in pairs. So the first one is physical harm from individual robots. Can individual robots cause physical harm to humans, animals, or the environment? Very straightforward question. Physical harm from the swarm. Can emergent swarm behavior cause physical harm to humans, animals, or the environment? So you can see that these are paired. You have physical harm from individual robots, physical harm from the swarm. Then you have robot behavioral harm. Now, bearing in mind, this is very high level. So, in a sense, Edmund and Sabine are making the distinction that you might have behaviors as opposed to the physical robots resulting in unsafe operation. Behavior of individual robots, and here, can failure of the emergent swarm behavior result in unsafe swarm operation? So again, these two come as a pair. And then finally, security. can individual robots in the swarm be maliciously hacked? Not good. And can emergent behavior itself be subverted? Now, the reason this is important and different to number 9 is because emergent swarm behavior might be subverted not by hacking at all, but by gaming. And what I mean here is human beings, for fun perhaps, just getting in the way of the robots and kind of quite literally subverting the robots' collective behaviors. So I think this is a really comprehensive and really nice set of safety principles. And this really is the starting point for this paper that I'm giving you the preview of this afternoon. So, how to design safe and ethical swarm systems? Well, I would say that swarm robotic systems must be designed using best practice for safety-critical real-world systems. That's the baseline. That's the starting point. Best practice, best engineering practice for safety-critical systems, because we're talking about physical systems in the real world interacting with either humans, animals, or the environment. Plus, so this is very important, in addition to that, we need frameworks for ethically aligned or values-driven design. And I'm giving here a couple of examples of frameworks for ethically aligned. In fact, this is the IEEE Global Initiative on the Ethics of Autonomous Intelligent Systems, which I was a part of, and I contributed to this publication called Ethically Aligned Design, published by the IEEE Standards Association 2019. And there's this beautiful work by my good friend Sarah Spiekermann in Vienna. You probably know of Sarah's work. If you don't, you should do, called Value-Based Engineering. So we need that on top of that. And I think we need an additional layer of measures to mitigate the safety issues that were listed in the previous table, the previous slide. So that's 2 extra things that I think we need over and above simply using best practice as a convention, from conventional systems engineering. And going back to what I said earlier, I'm repeating myself. Why do we need that extra stuff? Well, because emergence, autonomy, and what was the third one? Security, yes, yeah. That's right, scale, yes, thank you. I'm just going to take a sip of water, if I may. So, I'm now going to tell you a little bit about ethical risk assessment, which I think is the most powerful tool that we have in responsible robotics today for all robot systems. Now, Mohsen mentioned that I'm heavily involved in standards. I'm a bit of a standards evangelist, and I could give you whole talks about standards. I won't. And I was part of the British Standard Working Group that drafted and published this standard. And we think it's the world's first explicitly ethical, in the sense that the word ethics appears in the title of the standard, for robots. So we think it's the first standard ever published that actually has the word ethical in the title of the standard. So it's called A Guide to the Ethical Design and Application of Robots and Robotic Systems, but that's a bit of a misnomer. What it really is a method for doing ethical risk assessment. Now, risk assessment is not new. Of course, if you are doing any human robot interaction projects in your lab with real humans, you know that you have to get ethics approval for that. Very important. So what is the process of ethics approval? It's a process of risk assessment. So risk assessment is a very, normal thing that we have to do. And I mentioned I've worked in safety critical systems. We were doing risk assessment all the time. It's a really fundamental part of what we do. What 8611 does is it extends beyond conventional risk assessment to include ethics. And essentially, the standard sets out 20 distinct ethical hazards and risks grouped into these 4 categories: societal risks and hazards, application, commercial, financial, and environmental. And for each of these ethical hazards, we give advice on measures to mitigate the impact, to reduce the impact, along with suggestions as how you can actually verify that you really have mitigated. It's a very powerful method, and in fact, I've published with colleagues, I think 3 papers now of case studies for ethical risk assessment. And the most recent paper was actually presented at ICRA 2023 last year, and it was an ethical risk assessment of a hospital disinfectant robot. So, that's a real world robot in real world use in a critical environment. So, this really is a very powerful method indeed. Now, in the paper that I'm presenting to you, we have a number of case studies, and I'm just going to show you the ethical risk assessment for one of those 4 case studies. And this is the case study, and it's a courier swarm system for city logistics. Now, I didn't come up with this. This is Sabine's part of the work. But here she's imagining a whole bunch of robots, of courier robots that essentially can move stuff around, home to homes, to shops, from warehouses, from bakeries and such like, or to offices or from offices. So really quite a sophisticated system, swarmish, as it were. So not like the current courier robots, which are not swarmish. Current courier robots are better described as multi-robot systems. So no emergence or self-organization. Now, actually, I thought you'd be interested to see the other 3 case studies in the paper. I'm not going to show you the risk assessments, but we have firefighting aerial swarms. Of course, that's very close to Sabine's heart, because that was essentially what she worked on in her PhD at EPFL. We have pollution detection using floating swarm sensors. So that's an environmental kind of application. And of course, again, reflecting Sabine's work, more recent work at MIT and now in Bristol, on nanorobots potentially for cancer treatment. So you can see, we're talking about tens of robots here, probably hundreds here, thousands here, and potentially millions here. But the point is, this paper is essentially presenting a generic framework for ethical governance for all of these systems. Now, here is, in fact, the ethical risk assessment for the swarm courier example. And it's rather a busy table. I don't really want you to read all of it, but I just want to see you to see the structure of an ethical risk assessment. So typically, we have a column that has the category, and these are the categories from BS 8611. So physical, societal, privacy, security, environmental, and so on. You have the ethical risk, the level that you judge from medium, high, or low, there's a low there. And then the mitigation strategy. So you can see there's a physical risk of collisions or obstructions of important thoroughways, thoroughfares. There's a societal risk, which is lack of trust from local communities. Local communities really don't want the robots or are somehow disturbed by the robots. Then, of course, impact to employment. I mean, this you know, Sabine judges a high risk. This is a medium risk. But the mitigation here, of course, interestingly, is to focus on the swarm on unmet needs. So hand-to-hand deliveries and allowing users to ask for human delivery if they want it. So in other words, there's a kind of opt-out there. And then, of course, another societal one, inequality of access to the technology, and the mitigation would be government subsidies or investment toward the deployment of robots in every community, so that it's only not only favoured, as it were, rich communities, please. Yeah, no, you're right. I mean, I think it's important to note that ethical risk assessment is highly subjective. It's not a scientific process. But what I would argue, that it's better than nothing. It's better than no ethical risk assessment. In fact, it's way better than no ethical risk assessment, even though the process itself is highly subjective. And one of the ways that, in fact, you can, in a sense, mitigate the risk of the fact that it's a subjective process is by using the process iteratively with different stakeholder groups. And I'll come on to stakeholder groups and how important that is. So, you know, the worst people to do the ethical risk assessment are the engineers who design the system. Bad idea. For one thing, if you're an engineer, you've designed the thing, you love your system. You think it can't possibly go wrong. But, you know, really, this kind of ethical risk assessment needs a multidisciplinary approach with all of the stakeholders. And that means, it means local businesses, it means local citizens, ordinary citizens, you know, mums and dads and teenagers and old people especially, because they might benefit a lot, you know, from this kind of technology if, you know, if they can get their heads around it. So don't think of ethical risk assessment as a one-off process. It's an iterative process, please. I won't keep going down here, but you can see some interesting, you know, privacy, security, swarm collect sensitive information, swarm tasked with illegal operations, you know, the local drug cartels using the swarm to deliver, and environmental concerns, of course, swarm design not sustainable, and then, of course, overconsumption. You know, maybe we shouldn't be, I suppose it's too late. I mean, we already, you know, order stuff from Amazon as if, you know, there's no tomorrow. So overconsumption is kind of, we've lost that battle, I think, already. Anyway, I hope at least you get the idea. But if you are interested in ethical risk assessment, then, as I say, I've got a bunch of papers, I think 3 papers right now, with much more detailed risk assessments. I mean, one of the reasons this is tricky is because we think we're the first to even think about ethical risk assessment for swarm robotic systems. And of course, this table is actually a shortened list of what we should be listing. I mean, actually, a full ethical risk assessment would be much longer, because we've not covered here, for instance, the what was it? The legal aspect. You know, there are things that appear in Edmund and Sabine's safety principles that we're not covering here at all. Well, really, in the interests of brevity. So this brings me then to the final bit of the talk discussion, I hope, the proposed engineering framework for the ethical governance of swarm robotic systems. So, as I mentioned earlier, the framework is built upon a conventional engineering life cycle from conception. In other words, dreaming up this swarm robotic system to end of life. But we add a layer of additional ethical governance processes. And broadly, these processes fall into 6 categories. This is the additional layer that we're arguing is needed because of emergence, autonomy, and scale. The first one we've just mentioned a little bit: stakeholder consultation and governance. And you'll see when I start showing you the flow diagram where that comes in. Ethical risk assessment, I've just given you a very brief introduction to ethical risk assessment. Data logging. Now, I'm going to give you a couple of slides in a second, telling you a little bit more about data logging and why that's important. Human swarm interaction, I've already mentioned. Accident and incident investigation is another important property here. And in a way, these two are 2 sides of the same coin. The point is that, ethical risk assessment and accident investigation are 2 sides of the same coin, because if your ethical risk assessment is not guaranteed to find all of the problems, which means that even a perfectly ethically risk assessment system, there might still be accidents or incidents. An incident, I should explain, is a near-miss accident. And it's an accident that nearly happened, but didn't. And I'm going to tell you a little bit more about that as well. The reason I'm going to tell you more is because I've spent most of the past 5 or 6 years, actually, working on 2, 3, and 5 as part of a single big project. And number 6, the final bit of the layer, is end-of-life repurposing and or recycling. And I think that's, again, something we don't do in robotics, any robotics, let alone swarm systems. So, okay, so now I'm going to tell you a little bit about data logging. So back in, I think it was 2017, I and a colleague came up with the idea that all robots should be fitted with the equivalent of an aircraft flight data recorder. Simple idea. And we published this paper, The Case for an Ethical Black Box. Why? Why do you think robots need a data logger? Well, it's because just like an aircraft or a train or a boat or ship, for instance, if you do not have data, how can you find out what went wrong if there's an accident? You simply cannot. So it's a very simple idea. And of course, it's not a difficult thing to do either technically. But right now, no robot manufacturer puts a data logger into their robots. Yet, we have manufacturers selling social robots. We have manufacturers selling robots that are designed to interact with humans. These are accidents waiting to happen. The point is that, and we've argued this, accidents are much more likely now than they were 20 years ago, when the only robots around were in factories inside safety cages or in warehouses where the humans are kept out completely. Now we have an entire new generation of social robots, and that includes a vast range of robots from hospital assistant robots, from elder care assistant, independent living, assisted living robots, all the way down to smart toys. And in between there, you've got surrogate pets like the Parrot, robots that are used to mitigate trauma, for instance. So, we argue that there's a big problem. There's a much bigger probability of accidents and incidents, near misses with social robots than right now with industrial robots. Yes, please. Black boxes are actually orange anyway, so it's interesting, isn't it? But no, it's very interesting. You're quite right. And just to give you some comparisons, an aircraft flight data recorder right now records the most recent 17 hours of flight. 17, not 18 or 15, but 17. And that's because, at least the last I saw this, that was longer than the longest single flight an aircraft can take in the world. And you always record the most recent, N hours or minutes of data. Most event data recorders in conventional cars, not Teslas, record only the most recent 30 seconds. And the reason for that is because typically when there's an accident involving a vehicle, a lorry or a truck or a car, you don't need to know what was happening half an hour ago. You only need to know the very recent history. So now, I mean, I'm not arguing whether that's an appropriate amount of data, but we certainly propose that we call it an ethical black box because it would be unethical, irresponsible not to have one. That's the reason for ethical black box. In fact, you can actually record a lot of data. I mean, bearing in mind, memory is essentially free. And if providing you don't record video, but sample the video, take frames, a few frames a second, you can certainly get a lot of data into current storage, solid state storage. Or you can do the Tesla thing and stream it all to the cloud if you want. Although that does, of course, have privacy issues around it. And of course, and I should say that idea led to, actually it was more than a 5-year project because of COVID. I think it ended up a 6.5-year project called RoboTips with Marina Jarotka at the University of Oxford. And that was what the project was called. And essentially the project was had several objectives. One of them was to develop and kind of stress test, if you like, the idea of an ethical black box. I mean, conceptually, it's very simple. There's the EBB. And of course, the data connections with the robot sensors, AI and actuators is all one way. It's an entirely passive device as far as the robot's concerned. But of course, it should be collecting sensor data, typically compressed, actuator demands, high-level goals, alerts and decisions, ideally with the reasons for those decisions. And of course, you need a standard interface to connect and access the data. And so far, we've developed EBBs for, well, I say we have partners at PAL Robotics who are building EBBs for their robots, the Tiago and other such robots at PAL. The EPUC, of course, you'll be well aware of this. I still have a swarm of 50 of these that I used for most of my swarm robotics and Miro. And this is an exoskeleton, upper body exoskeleton developed by a spin-out company from the lab. And we developed an EBB for that as well. So, and in fact, because I thought you might find it a bit fun. And I forgot this slide, yes. So we also published a draft standard. You can see I'm a standards kind of nerd here. An open standard, an ethical black box for social robots. And in fact, we've used we based the standard on BS0, which funnily enough is a standard for standards. It's a standard setting out how to write standards. So you can tell how much of a standards nerd I am. But I thought you might be amused, given that swarm robotics is the subject of this talk. So the first EBB, in fact, I wrote myself, I developed it in early 2021. So this was deep in COVID lockdown. Of course, we couldn't get into the lab. I had no access to actual physical robots. So I basically used a robot simulator, VREP, it's now called Capilla Sim, with an EPUC robot. And I wrote some code. Actually, I taught myself Python. That was really the reason I did it. I wanted to learn Python because all my students write in Python. It's a horrible language, but I wanted to be able to read their code. So totally horrible language. Anyway, so I then wrote a kind of sockets, connection, TCP/IP connection between VREP, and was able to then, this is a video, you can see the robot moving. There's the EPUC in simulation, and you can see every second it's grabbing all of its sensors, infrared and joint angles and such like. So there's a simple example of a little EBB. So I thought I'd throw that in just as well, because otherwise there are no movies in the talk, and because that's the last bit of proper coding I did, which is very sad, I know. Okay, so I mentioned the RoboTips project, and another big part of that project was about accident investigation. And accident investigation, of course, is not just about needing data from a data logger. That's part of it. It's fundamentally a human process. It's a human process of discovery and ultimately reconciliation of kind of coming to terms with the particularly if it's particularly if it's a very severe accident. And we did something over the past 3 years in RoboTips, which I'm very proud of. I think for the first time ever anywhere in the world, we ran a series of mock robot accidents. Simulations, in fact, but real simulations with real robots and real human beings. And in fact, we had humans as subjects of the accident. In other words, the person to whom the accident happens. Of course, they weren't actually harmed at all. We had human beings as witnesses to the accident. And we also had, and this is important, volunteers to investigate the accident. So we weren't just simulating the accident, we were simulating the investigation of it. And we were very pleased, very lucky indeed, to recruit onto the team an expert, a world expert in accident investigation. He's actually an academic, he's not an accident investigator, but he's written many books on it. So he's as close as we could get to a real hardcore accident investigator. And typically we would add a couple of 1 or 2 student volunteers who would learn a lot. So interestingly, we simulated the accidents, but the accident investigations were effectively like a real. It was the same process that you'd use for real, using the same kind of methodology. And over the course of the last couple of years, since, of course, we could reopen the lab, we ran 3 accident investigations. In fact, we ran each one twice over. The first one was a kind of pilot or a dress rehearsal, if you like. And the second one, with a completely different set of volunteers, of course, because the first set of volunteers would know everything. They're not allowed to know everything, of course, except the subject. The only volunteer who knew exactly what was going to happen was the subject of the accident, because, of course, they want to be reassured. They want to, A, know what's going to happen to them, and B, be reassured that they're not going to actually be harmed. So this was an accident where we had a Pepper robot in our assisted living studio in the lab, which is a kind of granny flat. This whole structure is an entire apartment in the lab, with a living room and a kitchen and so on. And this person here, we were all wearing masks because this was, lockdown was over, but it was still, COVID was still around. And here is the robot. And essentially the story is that there's an elderly gentleman who's had a fall in his apartment. But the elderly gentleman has an assisted living robot. So the question that we posed to the accident investigators is, what happened to cause the fall? Was the fall just the elderly gentleman's fault, or was the robot partly to blame? Even if the robot wasn't involved in the fall, why did the robot fail to raise the alarm? So it was actually quite a complicated scenario. And you can see here, this is one of the accident investigators interviewing one of the witnesses, and inside there's another one interviewing one of the witnesses. So that was the first accident investigation. The second one was very interesting. They were all interesting, but this was especially interesting because here we had an accident causing psychological harm to a young girl. Now, of course, there were no young girls involved, and there was no real psychological harm. But the important thing about psychological harm is that there's no singular event. Whereas here, there was an event, the fall, that you can identify. It's obvious that there was a singular event, or perhaps several events, but all at the same time. Here, the psychological harm took place over a number of months, simulated. Of course, the whole thing was simulated. And the idea was that the Miro robot, which was the robot at the center of this, was hacked. And its conversational AI became very aggressive, and that caused psychological harm. So it was a particularly tricky one for the accident investigators, but they did in fact solve the case. And there's the team that was doing this simulation. And the third one, which was only earlier this year, and the final one, was an upper body exoskeleton accident I mentioned before. And here this was kind of a quasi-industrial accident where we have a volunteer, this guy here, Dan, I think it was, wearing the exoskeleton, and he's lifting real boxes high up onto shelves. I mean, the boxes were empty, but nevertheless, he's actually physically using the exoskeleton. And he has a fall and becomes injured. Again, not really. And as with all of the previous accidents, there was data from the ethical black box, except that in the previous accidents, we had to fake the data because we didn't at that point have EBBs for a Pepper robot or a Miro robot. We do now. But in the third case, we actually had real EBB data. And that was incredibly interesting. It was the first time we had data actually collected from the real, as it were, simulation. Now, not surprisingly, I don't believe anybody in the world has yet done a simulated accident involving swarm robots. So there's another idea if you're looking for projects.
The pandemic?
Sorry?
Pandemic depends on how you define robots.
That's true, yes.
Viruses, nanoparticles.
Yeah, that's very true, yes. It could be something even more difficult, as it were. Yeah, good thought. So what I'm now going to do, and I'm going to sit down again, is show you I love diagrams, being an engineer, of course. the flow diagram, and this is the first part of this proposed ethical system of ethical governance, and it's kind of color-coded. So the sort of purple bits are documents, specifications, in other words. The blue bits are all technical stuff, and the green bits are the extra layer of ethical governance that we've added. So you can see that the first phase is consultation requirements. And in fact, I've actually blown that up here so you can see it better. So here we have stakeholder consultation. This is a wide range of stakeholders, so it'll be the members of the public. It might even be, there might well be lawyers, there might be environmental people. There'll certainly be industry people as part of that, as well as the designers who are proposing this system. And that consultation might well say, okay, no, we don't want that. Thank you very much. Bad idea, go away. So that's very important as an outcome of a stakeholder consultation. If a stakeholder consultation doesn't have that outcome as a possibility, then why are they even bothering? Stakeholders need to have teeth in order for this process to work, to be really responsible. Then there's the development. Well, of course, the stakeholders are looking at the requirement specification, and kind of almost in parallel with this stakeholder consultation is the ethical risk assessment, which I've already outlined for you. And have the risks been minimized? No. Well, go back here and go around that loop again. And then, of course, the stakeholders should see the ethical risk assessment and actually be part of it. Because, because of the very broad range of stakeholders, they are perhaps more likely to think of things that engineers would not think of themselves. And only if the answer is yes to this question here, do we then move on to the next phase, which is the design and test phase. So here you have pretty much a conventional, design. You have design, you have simulation trials, you have against test specifications, you have real robot swarm and human swarm interaction trials in parallel with the simulation trials. You have verification validation, very important, and do the tests pass the V&V? Now, verification validation, of course, is very tricky for swarm systems. I wrote a bunch of papers early some years ago, I think in the late 2010s, when I was interested in how exactly can you verify swarm systems. And there are techniques, but they're quite tricky. So typically, I think the most powerful method that I worked on was a system called, an approach called probabilistic finite state modeling, which is it's a probabilistic approach, but again, like technical risk assessment, is better than nothing. So now here again, once you've done all of this, you redo the ethical risk assessment with the stakeholders again. So this is the second iteration of the ethical risk assessment. And of course, if this fails, then you need to go back here, review the system design. If it passes, then you're ready for deployment. And this is the second part of this big diagram. And here we have, on the left, fabrication and deployment. This middle bit is operational, so the operation of the entire system, and the shutdown phase. And this is the first part of that. Well, again, this comes in here. Stakeholder consultation during the robot infrastructure fabrication and test, because that, the important thing is that swarm robotic systems are not going to be infrastructure free, mostly. Some might be, but most will not. Most swarm systems are 15 minutes. Will need some infrastructure. So that needs to be built and tested. And stakeholders need to be part of that, because infrastructure, that means, putting stuff in the environment, which might be, it might be an urban environment, it might be a natural environment, it might be, something around a human body. So here are the specifications. Here is where you install the infrastructure, providing the stakeholders are happy, and then you can deploy the swarm. Oh, and of course, we need to train swarm system operators, and again, stakeholders should have an input to that. And we have operations manuals. So that then leads to the operational phase. And here, this big box, this is the swarm system is operation. It's actually running. And of course, it's being monitored by the human swarm interaction system, monitoring and intervention. This is the data logging. And of course, the data logging is not just logging data from the individual robots, it's also logging data from the infrastructure. And here you have a governance board, which has some of the same stakeholders on it, but this is altogether a little bit more serious, because they have a duty which the stakeholders don't have, which is in the event of accidents. So in the event of accidents, and this could be an accident or an incident, then the governance board will review the operation data and assess the severity of the accident. If the accident is very severe, then they will call for a full swarm extraction. In other words, the entire system is shut down, and then you have the accident or incident investigation, and you'll have some recommendations, and those will be fed back to the system, the previous stage, before the swarm robotic system can be relaunched. Of course, you will have individual robots that will fail or stop working properly, so those need to be extracted and reinserted. And then, of course, the other thing that's going on here is eventually the system will come to the end of its life, and you'll then head into the very final section, which is very straightforward, system decommissioning, and ideally either or both repurposing or recycling of the robots and the infrastructure in order to minimize, as it were, the amount of waste, electronic or other waste caused by the system being shut down. So that I've almost finished. So that is, to conclude simply that this is a draft framework, and I hope it's given you ideas, thoughts, and even suggestions. So please feel free to contact me if you think of anything, or even if you'd like me to help with any of the stuff that's going on in the centre. And of course, I want to credit the RoboTips team, because I've described a lot of RoboTips work as well as, and there we are. And there is a bunch of papers from the project, and I'll again, I can let you have a copy of these slides, so you can check out some of the papers. So we've written papers about pretty much all of the aspects of the work that I've described. So I hope you found that interesting. Thank you very much indeed. Thank you.